I'd like to welcome you to this video where I intend to go through the solution to the paper 1 of the year 2020 May-June session of physics subject, and this is advanced level. Now, before I get started, I'd like to give you a piece of advice on how to get the most out of my videos. Let me just reduce the percentage a little bit so that everything can be legible and well visible on the screen. Now, paper 1 usually has got 40 questions. And because I intend to go through the whole paper, you may not have a problem with every question, although I would recommend that you look at how I solve every question. So I want to make it easy for you to be able to navigate through the video and go to the question that you want. So I've put timestamps on this video. For example, if you go to the first timestamp, I'll be talking about this introduction part of it. If you go to the second timestamp, I might be talking about question 1. The other timestamp, question 2, and so forth until I reach question 40. Where do you find the timestamps? You find the timestamps on the scroll bar of the video. If you hover your cursor over the scroll bar of the video, you will find marks. Those are timestamps. If you skip to a certain mark, that is where I'll be talking about a particular issue, a particular question. The other way of getting to know where to find what is when you go to the video description. If you go to the description, there will be timestamps where I have clearly indicated that during this time of the video, I'm talking about this particular question. So that is something that you might want to capitalize in. The other thing that I want to make it clear is that the whole of this question can make the video to be very long. So I might end up splitting the paper or the video into 2 or 3 or even 4 videos so that they are short enough. But every video, I'll be careful to indicate the number of questions that it is addressing. Having said that, let's go to the first question. Now, when you look at this paper, the second page usually has a list of constants. The third page has got formulas and so forth, and the questions actually start on the 4th page. So let's get started with question 1. In this first question, we are asked to give a reasonable estimate of the kinetic energy of a car traveling at a speed of 30 meters per second. Throughout the syllabus, the examiners usually expect us to be able to put some meaning on the magnitude of certain physical quantities which we calculate. Because physics is about life and we are supposed to interpret life using the physical constants in it. Let's say, for example, you measure the diameter of a wire and you quote that diameter as maybe 0.34 meters, that is 34 centimeters. And someone else quotes it as 0.34 millimeters. You find that the one who quotes it as 0.34 millimeters is in any... The student who quotes 0.34 millimeters is likely to be correct than the one who says the diameter of the wire is 0.34 meters. Why? We know the size of a meter, and indeed, unless you are talking about an extraordinary kind of conductor, there is no conductor with that kind of diameter, 34 centimeters, unless maybe it is in a power station or something like that. So you find that why are we able to immediately recognize that something is wrong somewhere is because as we write down the magnitude of physical quantities, we are supposed to think about those physical quantities, not just quote an answer because you have worked it out. You may be able to tell that there is something wrong with this answer just by looking at the magnitude. And that is where this first question comes in. So what is expected here is for us to be able to recognize that maybe the car, let me just write, this is question 1. Got question 1 here. Now the mass of the car is around 2 tons. That is 2,000 kilograms. Let's see how I would work out the kinetic energy given that value. Kinetic energy of any object, of course, is a half times mass, which I've said is around 2 tons. Notice that that value comes in my mind because I know a normal car would weigh between 1.5 and maybe 3 tons. When it comes to about 10 tons, that one is a truck, and so forth. So a half m v squared. V squared is 30 squared. Manipulating these values, I get this one, I get 1000, and here I'm going to get 1.0 by 10 raised to, this is 900. In fact, it's supposed to be 9. It's supposed to be 900,000. So 9 by 10 raised to power 5 joules. Something like that. What is meant by the order of magnitude is this power here. Because again, the examiner don't expect you to be very exact, but you can give an estimate and say that this physical quantity, its magnitude lies between this value and this value. That is what they expect you to be able to do. So even this 9, I could approximate it to be 10. Approximately 10 by 10 raised to power 5. And this is approximately 10 raised to power 6 joules. And that is why the correct answer will be C. Now let's look at question number 2. Now this question is about homogeneity of physical equations. And what is meant, a simple way of describing homogeneity of physical equations is the use of SI base units to try and check whether an equation is correct or not, or to even come up with the correct form of an equation. So for you to be able to use that skill of homogeneity of physical equations, it is expected that you must know the units, especially the SI base units of the physical quantity of one side. For example, here, when we are given frequency is equal to a certain constant C, then we've got mass raised to power P, and we've got K raised to power Q. We know the SI unit on this side. The SI unit on this side is Hertz. But although Hertz is an SI unit, it is not an SI base unit. There is a difference between an SI unit and an SI base unit. SI base units consist of the kilogram, the second, the meter, the Kelvin, the mole, the candela, and the ampere. Those are the 7 SI base units. Any other unit is a named unit. For example, the Hertz is the name of a scientist, the Newton is the name of the scientist, the Coulomb, the Farad, the Pascal, all those units I'm mentioning, they are SI units, but they are referred to as base, they are referred to as named units. And in fact, we are expected to define them. When it comes to defining units, we are talking about definition of named units. Many times you may find a question asking you to define the Newton, define the Pascal. They're talking about definition of named units. Now, there is a simple way of expressing a named unit in terms of SI base units. And I'm going to use the Newton to do that, because the Newton finds its way around here. So the first equation here is written in terms of physical quantities, and they've told us that C is a constant which does not have any unit, so we are going to remove it in our equation. So the unit on the left hand side is the Hertz, which is also expressed as per second. The unit of mass is kilogram, and that kilogram is raised to power P. The unit of the spring constant is Newton per meter. Everything here is raised to power Q. You can see the kilogram is an SI base unit, so I leave it. The meter over here is an SI base unit. I leave it too. But the Newton is not. The Newton is defined from the equation force is equal to ma. So that when I say that 1 Newton is equal to 1 kilogram times 1 meter per second squared. Sorry. So over here, I'm going to have my kilogram raised to power P. And then instead of the Newton, I'll have kilogram meter per second squared, and there is another meter there. This one here, per meter. Everything in this section is raised to power Q. So I go on, I get my kilogram raised to P. I open the brackets and get kilogram raised to Q. This, you'll be able to see that meter and per meter cancel out, because per meter means 1 over meter. 1 over meter multiplied by meter, they are going to cancel out, and that one is gotten rid of like that. Seconds, on the other hand, is raised to -2, but when I open the bracket, it becomes -2 Q. Now, at this point, I would write the unit on the left, which is per second. This is kilogram raised to power P times kilogram raised to power Q. I would say it is kilogram raised to P plus Q. Just need to add their powers, times seconds raised to -2 Q. You can see that on the left hand side we don't have any power for, we don't have the physical quantity kilogram, but on the right we have 1. This is what you can do. I'm just going to insert kilogram on the left hand side like that, but then I will raise it to power 0. The reason I do that is because any number raised to power 0 is 1, and 1 times something is just that thing. In other words, now I want to start equating the powers on both sides of the equal sign. The power here, which is minus 1, is equals to the power here, which is minus 2q. So I can effectively say minus 1 is equals to minus 2q. If I divide both sides by minus 2, I will get my value of q to be equal to a half. And then, for me to get the value of p, I will have to equate the power for kilogram on the left, which is 0, to the power of the kilogram on the right, which is p plus q. And because I know q, I can say 0 is equal to p plus a half. Rearrange, and I get my p to be equal to minus a half. So my q is a half. Let's now look at the choices. My q is a half, so the answer is either this and this, while p is minus a half, and B is our correct answer. Let's go to question 3. Now let's read question 3 together. The power produced by a force moving an object is given by the equation power is equals to work done over time. Work is force times distance divided by time. And then we asked which quantities are scalars and which are vectors. This one should be very easy because on the side of scalars, displacement is not a scalar, so it rules out A. Power is a scalar, work is a scalar quantity, displacement is a vector, force is a vector, power again is a scalar, force is a vector, so it rules out C. Work is a scalar, time is a scalar, power is a scalar, but displacement is not. So you find that the correct answer for question 3 is B. Now, when you're doing multiple choice questions, there are those questions which are very easy to get the answer because you just need to recall and check in the table. It's like a checklist table, like this particular question. Always be careful when you're doing that question. Be very, very careful, but be fast. Careful in the sense that you don't get tricked and therefore you don't make mistakes. Very fast because we would like to save time for much more challenging questions. Like you can see, question 2 was a little bit more challenging and it may require more time than question 3. So you try to save time by going through easy questions very fast, especially those questions which just require you to memorize or to remember something. Usually move through those very fast with the intention of saving time for a little bit more difficult questions. So let's proceed to question 4. Now let's read question 4 together. A cathode ray oscilloscope displays a square wave as shown. The time-based setting is 0.20 milliseconds per division. That is a small division like this. What is the frequency of the square wave? At this point, we want to identify that point where this signal makes one oscillation. When I draw a displacement time graph, this displacement S, this is time, I would get a wave like this. This is usually the periodic time from here to here. It is a periodic time. Now, if we generate or convert this sinusoidal wave into a square wave, this is what we are going to get. We are going to have a situation whereby the whole of this occupies that. Over here drops to 0. And then it comes like this and like that. This line should have touched here. Right. So that one is a complete wave. So when we come to the square wave, a complete wave will start from this point all the way to some point here. And that is exactly what we have. Because if we draw our equilibrium line, which is here, we're starting from this point, coming like this, all the way to this point, which is this point. And this point is also this point. So that is a complete wave. So how many boxes does it take? 1, 2, 3, 4, 5, 6. So you're going to say it is 6 divisions, but each division represents a time of 0.20 milliseconds, of course, per division. So once the divisions cancel out, I'm left with milliseconds. So remember here I'm working out the periodic time, which is going to be equal to 1.20 milliseconds. The same as 1.20 by 10 raised to minus 3 seconds. And don't lose sight of what we are working at or we are looking for. It is a frequency, and the frequency we expected to remember that expression. It is 1 over the periodic time. So I'm going to get 1 divided by 1.2 by 10 raised to minus 3. So let's see what we get from there. So I'm going to get 1 divided by 1.2. First of all, just get that, then multiply it by 1000, because the inverse of this is just 1000, and I get 833. It becomes 833 hertz. And when I look at the choices, the closest one is B. So our answer is B. Like that. And let's go to question 5. Now, in question 5, we are told that a measurement is taken correctly, but with a ruler at a significantly higher temperature than that at which the ruler was calibrated. The higher temperature causes the ruler to expand. What describes the effect on the measurement caused by the higher temperature and how the measurement may be improved? So again, here is just a matter of going through the choices. And you can see there isn't any calculation to be done. It's just about being able to understand what we are looking at here and how we can get the correct choice. So the first choice is the measurement will be subject to a random error. The measurement can be made more accurate by taking the average of several repeated measurements. While this second part is correct, that kind of the expansion of the meter rule will give us a reading which is smaller, consistently smaller than the actual measurement. it will be smaller throughout whichever object or whichever repetitions we are going to do. That aspect that the measurement is consistently smaller than the actual value is what rules out the fact that this error is a random error. It's not a random error, it is a systematic error because of its characteristic. B, the measurement will be subject to a random error. Again, we rule out that because of what we have said. C, the measurement will be subject to a systematic error. Now, that one is correct. Let's see whether the next section is correct. The measurement can be made more accurate by taking the average of several repeat measurements. We cannot improve a systematic error by taking repeat measurements and finding averages. That method of taking repeat measurements and finding the average usually works for random errors, because there is a time a measurement will be greater than the actual value, sometimes it's smaller than the actual value, and when you do repeat measurements, there is a chance some of your measurements will be bigger than the actual value, while others are smaller than the actual value, and when you find the average, it brings you now closer to the actual value. That is how you would solve or you would reduce a random error. Let's look at D. The measurement will be subject to a systematic error. Correct. This one is correct here. We said this is correct, but its solution not correct. The measurement can be made more precise by taking the average of several repeat measurements. There's something I need to explain here. Accuracy and precision. Accuracy is how close a reading is to the actual value. Accurate values are usually the difference between the measured value and the actual magnitude is usually very small for accurate measurements. Now, precision is about the number of significant figures. Now, we have seen that we cannot improve the precision or reduce that error by repeated measurements and taking an average. We cannot do that. In other words, the only way we can reduce this error here is by changing the instrument, or by making sure that we take the measurement at the temperature at which the steel rule was manufactured. Whether it is a steel rule or a wooden rule, there is a temperature at which it was manufactured. But now it is being used at a temperature higher than that temperature where it was manufactured, and therefore it becomes longer. If it becomes longer, every measurement becomes slightly longer. That introduces an error into the measurement. That kind of error can only be solved by removing that which is introducing the error, and that is temperature. Lowering the temperature so that the meter rule can contract. It cannot be solved by changing the instrument, because even the other meter rule will come in with the same kind of error. But here they have not addressed the idea, in part D, they have not addressed the idea of making the reading to be more accurate. They have left that one out, which would be solved by changing the instrument, or not changing the instrument, but rather changing the conditions which are introducing the error, and that is lowering the temperature. They have gone over to precision, so we need to understand what precision is. How do we improve the precision of a measured value? So the measurement can be made more precise by taking the average of several repeat measurements. That is true. If you take the average of several measured values, it will not do anything to the accuracy, because this is a systematic error, but it can improve the precision. So that is how you would solve that kind of question, and therefore 5D. Notice how I'm tackling out questions which do not require me to calculate anything. I am armed with knowledge of that particular area, and that is why you should learn how to make short notes for every topic, so that you know what are the most important concepts the examiner is testing. So let's go to question 6 and see how it looks like. Okay, let's read it together. The velocity of an electric car changes as shown. Of course, it changes with time. What is the acceleration of the car? Let me just state out right from the word go that the moment you see a velocity time graph or motion graphs, the examiner wants you to use two things: gradient and area. When it comes to velocity time graph, there are two things that are important. The area between the graph line and the time axis gives us the displacement covered by the object, or the displacement of the object, while the gradient gives us acceleration. So again, that one is some knowledge which you are supposed to have. So over here, very quickly, in my calculation, I'll say A is equals to the gradient, which is change in the quantity on the y-axis, divided by change in the quantity on the t-axis. So over here, we've got the velocity, and I think I can go to the maximum velocity here, which is this line here, just one division after 100. And it appears as if each division here is 5. Is 5, because there are 10 divisions between 100 and 50. That means 50 kilometers per hour. Therefore, if I divide that one by 10, I get each space here represents 5 kilometers per hour. So this is 105, while this is 0. So to get the change in velocity, it is 105 minus 0, which will give me let me just write 105. Okay, let me just write 105 before I convert them into meters per second, because I need that. So 105 minus 0 kilometers per hour is just 105 kilometers per hour. And the time it takes is all the way up to 4 seconds. 4 seconds. So 105 kilometers per hour is like 105 divided by 1 hour. So what I would do, I would convert 105 into kilometers into meters by multiplying by 1,000. That gives me meters, and 1 hour into 3600 seconds. And you can see I've got now my answer in meters per second. So I'll go up there, and instead of 105, I'm going to have 105,000 divided by 3600 divided by 4. And this should give me the acceleration. So I have 105 and I have 7.3. 7.3. Like that. And that is D. So the correct answer for question 6 is D. So that is how you work out. So 3 things that I want to emphasize here. For a velocity time graph, they can ask you to calculate the displacement without telling you that it is obtained by the area between the graph and the t-axis. Remember that. The gradient represents the acceleration. Again, they just ask you to calculate the acceleration without telling you how it is done. They expect you to know, because in the syllabus they have said students should be able to recall that the gradient of a velocity time graph gives acceleration and the area below the graph gives displacement. The other thing is how you do simple conversions of kilometers per hour into meters per second. You just write it as a simple fraction. 105 kilometers per hour is like 105 kilometers divided by 1 hour. You convert each one of these into SI units. How do I get this? I multiply this by 1,000 because I know this one here, that in 1 kilometer there is 1,000 meters. I also know that in 1 hour there is 60 minutes, and in 1 minute there is another 60 seconds. So in 1 hour there is 60 times 60 seconds. After using this one for quite a long time, I'm able to just come up with this, which is very easy. That's 600. That is how you would work out question 6. Let's go to question 7. So, this is about projectile motion. We are told that a projectile is fired from point P with velocity v at an angle theta to the horizontal. It lands at point Q, a horizontal distance r from P after time t. So you are given the path of the projectile, which is referred to as the trajectory. Now, the acceleration of free fall is g. Air resistance is negligible. Which equation is correct? Now, this is where you need to recall several things. One of these is this. This is the, let's say the y-axis, or physically the height, the way it looks like. This is the horizontal distance covered by the projectile. When the projectile is fired like that with the velocity v, usually we use u, but let me use the symbol that has been used. It follows that path until it strikes the ground at that point. We go ahead and resolve this into horizontal component of the velocity, which is v cos theta, and we get the vertical component, which is v sine theta. Forgive my handwriting there because my graphics tablet is not in a very good position. So this is the range. That range is usually given by this speed, the horizontal component, v cos theta, times the time of flight, which in this case happens to be t. That one is a correct equation. So I check whether we have anything like that. I've got r is equals to this minus that. R is equals to v cos theta times t. Immediately A is correct, and I do not need to proceed with any other equations which I have here. I simply proceed to the fact that I have seen a correct equation that corresponds with what I know. Now, how did I know this? I know this again from the knowledge that in projectile motion, the horizontal component of the velocity remains constant throughout the motion. So since it remains constant, any horizontal distance covered must be equal to that constant speed times time of flight. I use a very simple equation. Speed is equals to distance over time, and therefore distance is equals to speed times time. So if the speed is constant, then that horizontal distance is just equal to that speed times the time. So, like I said, this question was rather open, but there is some guidance. When I look at it, all of them are calculating r, horizontal, the range. So at least that one solves the problem. because the other one would have been to try and start calculating the height and so forth. If there was a question about the vertical height, then actually we would be able to move into so many other equations. But don't get confused here. Even when you get a question like that one, there must be some knowledge which you rely on. And this is in projectile motion. And in physics, we only deal with the horizontal projection, although projection at an angle comes from time to time. But the same concepts are used. So in horizontal projection, what is it that you must remember? You must remember that the horizontal component of the velocity remains uniform. So in order to get the horizontal distance covered, multiply that constant velocity by the total time of flight, and you get the answer. That's how we work out question number 7. Let's go to question number 8. Okay, let's read question number 8 together again in order to get the situation, how the situation looks like. A car accelerates from rest in a straight line with a constant acceleration. So it starts from rest, u is equals to 0, and it's got uniform acceleration, meaning that its velocity is increasing uniformly with time. Which graph best represents the variation of the momentum p of the car with the distance s traveled by the car? So let's see, this is the car. Its initial velocity is 0. It has an acceleration which is constant. So it has an acceleration which is constant. Let's see how the velocity time graph looks like. Its velocity time graph will be a straight line through the origin. It will be like that. In other words, the velocity is increasing uniformly. If I find the gradient of this graph, I should get the acceleration. But this time, they want us to talk in terms of momentum, which is given by mv, mass times velocity. And remember, the symbol of momentum is p, so p is equals to mv. Okay, so how does the momentum, instead of the velocity, change with the displacement? Yeah. So over here I can say this is momentum. Of course, this is mass, which is a constant. This is the velocity. I want to write the velocity in terms of the displacement. So I can say the final velocity is going to be equal to initial velocity plus 2as. Of course, the equation s is equals to ut plus half at squared, v is equals to u plus at. Those equations are equations of uniformly accelerated motion, motion where the acceleration is uniform. And you can see this question is about motion where the acceleration is uniform. So I've chosen this because I want to see how the velocity changes with the displacement, so that I can be able to replace this velocity here with displacement. So u is 0, so I'm going to have v squared is going to be equal to 0 plus 2as. And after this, I want to make the v to be the subject. So v is going to be equal to 2as everything square root. Now, because this is a constant, square root of 2a, that one will be a constant. I have to multiply that by the square root of this variable, the displacement. So that is how the v looks like. So I can come here and put, instead of v, I put 2a square root, then times square root of s. Now, if you plot a graph, this kind of graph, how will it look like? That's why now we come to here, because we want to know, does it look like this? does it look like this? Because obviously our answer is either A or C. A or C. So our equation, we have said P is going to be equal to, the constant here will be m square root of 2a times the square root of s. And you can see that if I plot a graph of P, momentum, against the square root of the displacement, I will get a straight line through the origin. It will be a straight line. So don't be cheated by this, because this S here is not a square root. It's out. But this is a square root. Now, if I plot a graph of y is equals to x squared, when I square, I get this kind of graph, like this. But again, this is not s squared, so it leaves me with A, and therefore my answer is A. So question 8, A is the correct answer. And let's go to question 9. Now, in question 9, what are we told? In question 9, we are told that the resultant force F on a raindrop of mass m falling with the velocity v is given by the equation this. So F is the resultant force, where k is a constant and g is the acceleration of free fall. What is the velocity of the raindrop when it reaches a constant velocity or terminal velocity? Now let's look at the situation, and we use this question also to review other situations. Here you've got a raindrop. Initially, upon release, the only force that will be acting on it will be its own weight, and it will be acting on it vertically downwards. But as time goes by, there will be another force which will come in, which is the air resistance, and therefore the resultant force on it, which is given by F is equals to ma. This resultant force will be mg minus the friction, which is equals to ma. That is how we can get the resultant force. So you can see that the resultant force is going to decrease, because friction, air resistance, depends on the speed. At least you can say approximately depends on the speed, but it is usually speed squared. Although that knowledge is not required, but you should be able to understand that when you have an object falling through air with higher and higher speed, the air resistance is going to increase. So with that knowledge, you will be able to see that because the speed of this raindrop is increasing downwards, the frictional force, air resistance, is going to increase. The resultant force, this quantity here, is going to decrease, and therefore the acceleration will decrease until a point comes when this friction is equal to this. When mg is equals to the friction, or when friction is equals to mg, then A will be 0. And it is at this point that it moves with terminal velocity. And we know this situation very, very well. So this is how the velocity changes with the time until it reaches terminal velocity, which is horizontal. So this terminal velocity, Vt. For here, the acceleration is reducing because the gradient of a velocity time graph is acceleration. And you can see the gradient is decreasing until it reaches this particular point. That is the theory behind this kind of question. Now we are asked, what is the velocity of the raindrop when it reaches a constant velocity? In that case, we have already said that when mg is equals to fr, so that is where I want to state that over there, our mg is equals to kv squared. kv squared. Where that is because the resultant force has become 0. So we want to make a velocity to be the subject. Velocity is going to be equal to mg over k square root, everything square root, and mg over k, everything square root, and our correct answer is C. Notice that the way I'm working these questions, I'm using certain facts that we have been able to learn. I'm also emphasizing on what the examiner is telling us. And the examiner is very good at telling us the correct information, resultant force. So what do you do with the resultant force? You must know resultant force produces acceleration. And that is why I wrote F is equals to ma over there. And then that leaves me now to imagine how the ball is moving. It's falling downwards, but its velocity is increasing. And then suddenly I ask myself, is it falling through air or through vacuum? It is through air, so there must be air resistance. And air resistance increases with the speed. Therefore, that quantity that represents air resistance must be increasing. So there are other things that you could review in this particular question. Are things which pertain to what happens if, for example, this one was a parachutist and the parachute opens. What happens if the object is falling through vacuum? How will that graph be different from this one? But anyway, we can look at that when we look at other questions. Let's look at question 10. So in question 10, we are given that a stationary toy gun fires a bullet. Which statement about the bullet and the gun immediately after firing is not correct? You see here, you cannot start working out that question unless you look at the choices. Yeah. But when you do that, now when you read the question, there's certain information which comes into mind. I know this question is about momentum. It's about, a reaction. It's about Newton's second law. It's about Newton's third law. So let's see which statement is about those laws is correct. So I arm myself with the correct knowledge about collisions and momentum and all that. So let's see. Number 1, the force exerted on the bullet by the gun has the same magnitude as the force exerted on the gun by the bullet. That is correct because it is Newton's third law. By the way, when they ask you to state Newton's third law, always state it in a very simple way. I usually discourage my students from stating action is equals to reaction because that one is a very open statement. Usually state it this way. If body A exerts a force on B, body B exerts a force of equal magnitude on A but in the opposite direction. Very simply put. B, the force exerted on the bullet by the gun is in the opposite direction to the force exerted on the gun by the bullet. That is correct because it's about the direction of those forces. They're just emphasizing Newton's third law. The gun and the bullet have the same magnitude of momentum. The gun and the bullet has the same magnitude of momentum. Yes, magnitude, yes, but their directions are opposite. The momentum of the bullet and the momentum of the gun, rather the gain of momentum of the bullet and the gain of momentum of the gun, they are equal but in the opposite direction. because the rate of change of momentum of the gun is equal to the force exerted by the bullet on the gun. And the rate of change of momentum of the bullet is equal to the force exerted by the gun on the bullet. And in part A and B, we have already agreed that these forces are the same. So if you remove time from both sides, you find that the change in momentum of the bullet and the change in momentum of the gun, they are equal but in opposite directions. Let me look at D. The kinetic energy of the gun must be equal to the kinetic energy of the bullet. In other words, here you are trying to tell me something about energy, but I know in this collision, kinetic energy is not conserved. It's not conserved. So I know the statement which is not correct must be statement D. Let me just verify that, because I'd like a situation where the answers which I'm giving you, that is question number 10, and indeed it is D. Let's go to question number 11. So there you have it. That is the first 10 question. You agree with me that all the 40 questions cannot be addressed in the same video, because that video will be very, very long. So I intend to cover this paper in 4 videos. But even before I complete the whole paper, if you like the way I teach, and you would like to know a little bit more in a situation whereby I'm able to reach you at home in the comfort and safety of your own home, and you are able to see my blackboard, you'll be able to see the question, you'll be able to see and hear as I explain, then get in touch with me so that you can be able to participate in what we refer to as online learning. It is not something that is difficult. All you need to have is a computer. A laptop would be enough, because I'd like you to have a situation whereby the screen, what you're looking at, is big enough and we're able to communicate. Otherwise, go and leave your comments below. Say something. If there is a topic you'd like me to address, or a question, a particular question that you'd like me to address, just write in the comments below. Otherwise, in my next video, I'm going to tackle the next 10 questions. That is question 11 to question 20. Until then, bye-bye.